Compliance, the final frontier. Tom Fox is the voyager of trekking through compliance. His mission? To explore the original series and seek out and share what it can teach you about compliance. Here's your host, Tom Fox.
Hello, everyone. This is Tom Fox. I'm going to be doing several follow-on podcast special series based upon my summer series of Trekking Through Compliance. Today, we start a 5-part podcast series on some of the science around Star Trek. In this exploration, I'm joined by my good friend Ben Locwin. Ben is a healthcare futurist, and he's also an astrophysicist, so he's uniquely situated to talk about the science of Star Trek. We had a lot of fun producing this series, and I hope you will enjoy it, listening to it as much as Ben and I did bringing it to you. In this episode 1, we take a look at the episode Mirror, Mirror, and use it to discuss transporters. Hello, everyone. This is Tom Fox. And as you know, I have been doing a summer series, Trekking Through Compliance, where I've been looking at Star Trek, the original series, the 79 episodes, and mining them for lessons around compliance and leadership. Well, for the next 5 podcasts, we're going to take things in quite a bit different direction, as I have with me Ben Locwin, and we are going to explore some scientific issues. So we're going to take a look at the stories of some of the episodes from the original series, and then Ben is going to consider whether or not the science is valid, the science is real, or whether the science could be valid or real. And where this goes, frankly, nobody knows. So Ben, with that incredibly long-winded introduction, I've been looking forward to doing this for a long time, so welcome.
Thanks, Tom. The pleasure's all mine.
So Ben, we are going to start with our first episode today, and we're going to use the episode Mirror, Mirror to ask some questions about transporters, artificial gravity, quantum superpositions, tunneling, and particle properties. So I'm going to give you the basic storyline or story synopsis, and then I'm going to ask you to talk about some science. So here we go with the story synopsis. After Captain Kirk fails to convince the Halcyon Council to allow the Federation to mine dilithium crystals on their planet, the landing party returns to the Enterprise. Interference from an ion storm, however, causes the landing party to be transported into a parallel universe and a mirror image of the Enterprise. Now aboard the Imperial starship Enterprise, the landing party discovers that crew members who are mirror images of themselves and belong to an evil federation known as the Empire. No doubt it will strike back one day. The first experience is the torture of the transporter operator, Mr. Kyle, with an agonizer for his alleged failure to beam the landing party up quickly enough. Immediately, Kirk realizes that a mirror image landing party must have also beamed aboard the real USS Enterprise, or perhaps I should say the one in our universe. Kirk, Uhura, McCoy, and Scotty impersonate their mirror image counterparts while finding a way to return to their universe. Kirk learns that he has been ordered to annihilate the Halcyons, but piques Commander Spock's curiosity by ordering the Enterprise to hold fire for 12 hours. While Scotty is adjusting the transporter to return them back to their universe, Kirk meets Marlena, the captain's woman. Meanwhile, the alternative Spock has received a directive to kill Kirk if he does not carry out the order on the Halcyons. Marlena then shows Kirk the Tantalus field, which he had recovered from a lost civilization, and uses it to eliminate his enemies. When Kirk and the party are ready to return, the alternative Spock knocks out, or rather does a mind meld with Dr. McCoy, and he ascertains what has happened. Discovering this switch, the alternative Spock then assists Kirk in returning his landing party to their universe so the Empire landing party may return to its universe. When Kirk and the party return to their universe, they find the Empire counterparts were immediately recognized and put into detention. so all is saved. So there's a lot of science going on here, pseudoscience, maybe science, or something else. Ben, where do you want to start?
There's a lot to unpack here, Tom. I think, let's start with the teleportation aspects of the transporter. So here's where we are with science fact at the moment. So as far as transportation, that's something that we can't do the way they do in Star Trek with the transporter. But what we have done, surprisingly and very interestingly, is we've done quantum teleportation. And what we're actually doing is transportation of information and not matter. And I think that's the big distinction. So we can transform information from quantum particles and teleport that from one location to another. And what we're actually teleporting is typically a binary bit, like what's called the particle's spin, whether it's spin up or spin down, or if it's horizontally polarized or vertically polarized, like in the case with a photon. So, at the moment, we are not quite at the point where we can teleport people from one location to another. And right now, it really appears that what you would have to do in order to do that in the future would be something that's not really teleportative the way we know it, but more recreative. So what we can do is we can recreate particles in another location and use the transferred information to essentially rebuild exact copies of the initial particles. But what you need to be able to do in that sense is have some kind of mass at the other end that you're encoding that information into, so that it could then transform into an object or a person, let's say, in the case of the transporter.
When you were going through that, Ben, my mind actually went back to the 19th century when we first began to use commercially telegraphs. And as I recall, a telegraph was a transmutation of a word or letter into a symbol, and then made into an electronic signal and transported. Is the kind of quantum transportation you're talking about advancing along those lines, or is that something different?
Yeah, that's an interesting analogy to use. So the telegraph, is indeed transforming some sort of information into an electrical signal. And what we're doing is essentially measuring the properties of a subatomic particle and then revealing those properties at the other end. And like I said, we can then transfer the information in a teleportative way, but what we can't do right now is actually have a physical particle pop out of nothingness. And that seems to violate what we know about the conservation of mass and energy in the universe. You can't just have matter spontaneously appear at any large scale, at a distance from the initial source. Interestingly, we've gotten to about 1,400 kilometers right now for space-based experiments of quantum teleportation. So a lot of this field is still pretty nascent. Charles Bennett was a fellow who worked with IBM, and in 1993 he coined the term quantum teleportation. And a lot of quantum cryptography and quantum computing relies on some of the principles within quantum teleportation. So it's not something that exists in science fiction anymore. This is actually current reality, and what are called qubits, and those are spelled Qubits. Those are the basic units of quantum information that are essentially information transfer through the teleportation process. There's a professor who was at least formerly associated with the University of Vienna, Anton Zeilinger, and he and some of his colleagues were some of the first to do experiments on teleportation and understand the ramifications of it. Now, like I said, what seems to be the case now is this can be observed with subatomic particles. There's some reason to think that up to molecular-sized objects can be teleported. One of those such objects is what's called a Fullerene, and it's a 60-carbon molecule that looks kind of like a cage. It's basically in the structure of a soccer ball, where it has a bunch of pentagons that are connected around a uniform sphere. And so you've got basically 60 carbon atoms in a soccer ball configuration, which is relatively massive for something that's in some sort of superposition or maybe teleportable. Interestingly, though, it seems like, and this is still one of the cardinal mysteries that exists in quantum mechanics, at some point, as things get larger and larger scales from the subatomic realm, it seems that these quantum effects somehow blur away and disappear and bring about the classical realities that we're familiar with, where we don't have cars and humans teleporting and people existing in two places at one time and things like that.
Ben, I grew up during the Apollo missions, and I was certainly aware of and really enjoyed the space race and all of the events around not only the original landing on the moon, but this 50th anniversary that we just had. One of the things I recall about the Apollo program that struck me then and always stuck with me was the communications that was utilized, at least on the public communication, that we would hear over the television, and how powerful the communications tools were with radio signals when Apollo came about, as opposed to Gemini, which was just rockets in orbit around the Earth. In listening to the various podcasts and other reflections of the 50-year history of the moon landing, I learned that not all of the communications were as smooth as I had originally had thought. So I was wondering, do any of these concepts around quantum transportation of information or data, do they relate at all to the radio signals that were used in the original Apollo missions?
No, they're somewhat different. So I think here's the distinction. So if we talk about the types of radio antenna that are used, they're essentially what everybody would be familiar with, but they're essentially much more focused or, much more powerful at their source. And what they're doing is transmitting an electromagnetic field. So it's the radio portion of the electromagnetic spectrum. So you have relatively long wavelengths, and they travel at the speed of light. And so, for example, the moon is about 1.25 light seconds from the Earth. So it takes a signal about 1.25 seconds to get from the surface of the Earth to the moon, or from the moon back to the Earth. And that's covering a distance of about 230,000 miles. In contrast, something like Pluto, which is no longer a planet, it's a dwarf planet now for the last, 14 or so years. It takes light about 7 hours to get from the Earth to Pluto. And so, those distances are covered at the speed of light. Now, the interesting aspect of quantum teleportation is there seems to be information, there's a communication between particles that are in what's called a superposition that is getting transferred what appears to be faster than light. And this was something that Einstein was never comfortable with. He called this spooky action at a distance, meaning you've got two particles that could be separated by an arbitrarily large distance. And when something happens to the first particle, if they were created in a specific sort of way that they were called entangled, if you separate the two particles by any arbitrary distance, even across a galaxy 100,000 light years away, whatever you're doing to one particle, its originally entangled partner particle also modifies similarly. And it seems to happen essentially simultaneously, so regardless of the distance between, there's no light transit time. And that's still something that there's not really a great explanation for. There are some models and there's mathematics that explain that seems to be happening, but the underlying mystery there is still to be uncovered.
Well, Ben, unfortunately, we are near the end of our time, but this has been a fascinating discussion of some of the science around the episode Mirror, Mirror. I look forward to continuing the conversation.
Thank you, Tom. My pleasure.
If you enjoyed this episode of Trekking Through Compliance, you can help it grow by sharing it with the biggest Trek fan you know.